Today, I'm going to show you an example of the Bellman-Ford algorithm. After watching this video, you'll know exactly how to run Bellman-Ford on a weighted directed graph. If you want to learn the theory behind Bellman-Ford, please be sure to check out my other video. We'll start with a quick look at the pseudocode. A few important notes. At most, we'll iterate v minus 1 times, and at each iteration, we'll update along all edges. Feel free to pause the video if you need more time. We'll use the following graph for our example. Notice there are 6 vertices, so we'll need to do 5 iterations. S will be our starting node. To begin, we'll make a table on the right to keep track of distances. We set 0 as the distance to S and infinity for the rest of the nodes. We're ready for our first iteration. Remember I said at each iteration we need to examine all the edges. I think an organized way of doing this is to look at each node one by one and examine its outgoing edges. When we've done this for every node, we're guaranteed to have seen all the edges. In our case, we'll start with S and work our way to the right. Looking at S, we see we can reach A with a cost of 10 and E with a cost of 8, so we'll update the table. Next up is A. We now know that we can reach A with a cost of 10. Looking at its outgoing edges, we see we can reach C with a cost of 2, or a total cost of 12. Getting to B, we notice we don't even know how to reach it yet, so we can skip this node. Moving on to C, we know that we can get to C with the cost of 12. Examining its outgoing edges, we see an edge to B with the cost of negative 2. We update the table. On to D. Again, we don't know how to get there yet, so we can skip it and move on to E. E has one outgoing edge. We now know how to get to D with the total cost of 9. We're finished with iteration 1. We start the second iteration by again looking at S. Notice its edges don't improve our distances, so we don't update the table. Same thing with A, B, and C. Their edges don't improve our shortest paths, so we don't update the table. Looking at D, however, we notice that its edges improve the path to A and the path to C. Starting at 9 and adding negative 4, we can now get to A with a cost of 5. And starting at 9 and adding negative 1, we can now get to C with a cost of 8. We update the table and move on to E. But again, we note that its edge does not offer any improvement. We're done with the second iteration. I hope by now you see the pattern. I'm going to let iteration 3 run without the voiceovers. Here's our shortest path values after iteration 3. We're ready for iteration 4. As we progress through the nodes, notice that none of the values in our table are changing. We finished iteration 4 and all the values are the same. Why is this? Well, the algorithm takes at most v minus 1 iterations, but we can make it more efficient by stopping early if nothing improves during an iteration. So, after 4 iterations, we're finished. Our table shows the shortest path from S to all other nodes. Don't be worried if your values at each iteration are different. A lot depends on the implementation and the order in which the edges are visited. You may even need 5 iterations, but I guarantee you will end up with the same result. Here's the pseudocode one more time. The time complexity is big O of v times e, which you can easily deduce from the code. Thank you for watching. I hope you now know how to run Bellman-Ford. If you have any questions, be sure to ask them below. I'll do my best to answer. If this video was helpful, please consider giving it a thumbs up and subscribing. Thank you.